The simultaneous acquisition of EEG and fMRI makes it possible to leverage the high spatial resolution of fMRI and the high temporal resolution of EEG in the same experiment. However, one major disadvantage of the EEG-fMRI technique is the abundance of artifacts in the EEG recordings, in particular BCG artifact. BCG artifact arises due to head motion as well as cardiac rhythm-related pulsation of scalp blood vessels inside the scanner. Although the latter movement is minor in scale, due to the presence of strong magnetic field, the movement of vessel and consequent electrode movement can induce voltage changes around tens of microvolts, which is larger than some of the common local field potential rhythms in the EEG signal. Moreover, BCG has frequency contents in delta, theta, and alpha band, preventing filters from being used. We introduce a new open source deep learning toolbox, BCGNet, for robust BCG artifact reduction. Using deep learning has multiple advantages. It requires no additional hardware and can learn the association between ECG and EEG directly without the need for QRS detection. Furthermore, deep learning can outperform traditional machine learning approaches in terms of association learning due to higher model capacity. BCGNet has the following features. It can train based on pre-optimized models or custom model defined by user, and supports cross-validation. After the training is complete, it provides quick tabular and graphical summary of model performance. It also supports loading data with alternative methods such as OBS for evaluation purposes. The setup of BCGNet is simple and straightforward. First, install the required dependencies such as TensorFlow. We recommend using Anaconda to simplify dependency management. CUDA can be optionally installed to take advantage of the GPU power. The user then needs to specify the input-output paths for the data, as well as hyperparameters. BCGNet provides a simple and minimalistic user interface. To reduce the BCG artifacts in EEG signals, simply initialize the session, train the model, evaluate the performance, and save the cleaned data. Let's take a closer look into the internal pipeline. BCGNet first downsamples the data and standardizes each channel to have zero mean and unit variance. It then splits each trial into 3 seconds long epochs and rejects outliers based on median absolute deviation. For each subject, it pulls the remaining epochs from all trials and shuffles them before randomly categorizing all epochs into training, validation, and test sets. It then trains a recurrent neural network on the training set. Training of a network will stop after either reaching the specified number of iterations or after loss values calculated on the validation dataset stabilizes. For evaluating the performance of BCGNet, we used the OBS algorithm separately and extracted the same test epochs from the EEG data. The results denote that BCGNet clean EEG shows lower power spectral density in theta and alpha frequency bands when compared to raw and OBS clean EEG. In conclusion, BCGNet embeds an effective deep learning-based approach into a user-friendly, standardized, and platform-independent toolbox to suppress BCG artifacts. It offers comparable power reduction in the delta frequency band and significantly higher reduction in the theta and alpha bands compared to OBS method. It also provides improved across-trial ERP consistency as well as improved classifier performance measured by AUC of the ROC curve.